through the project workflow that integrates macroscopic, mesoscopic, microscopic, and hybrid simulators in Aimsun Next 20. Of course, this will include several hands-on exercises where we will see how you can combine different levels of network loading in the same model file. Let's get started! After launching the Aimsun Next software, select the Tutorials tab. From the drop-down menu, select the tutorial Integrating Macro, Meso, Micro, and Hybrid Simulations. At the bottom of that window, select the documentation that guides you with step-by-step instructions through the exercises. Then, select the initial network. A new window will open named Select Existing Directory, where we will have to set the directory to store the available folder structure regarding this network file. I will select the desktop. In exercise 1, we will use the macroscopic simulator to assign the number of trips to both origin-destination matrices for two different vehicle types, car and truck, throughout the traffic network. The resulting assigned volumes will be compared to the observed data after creating a real dataset object as a sense check to verify that the data has been imported correctly. So we have opened already the ANG file. The next step is to create a real dataset object to retrieve traffic measured detector data to use for validating our eventual results. In the project folder, right-click, select New, and then Data Analysis, and then Real Dataset. A Real Dataset object has been created under the folder Real Datasets under the folder Data Analysis. Double-click on it and rename the object to Detector Data from 6 to 10 AM with a resolution of 15 minutes. Then select Add to add a retriever. A real data simple file reader will be sufficient. Then double-click on the Real Data Simple File Reader editor. Press on these three dots to open the external file containing the detector measurements, with a file which is called Detector Data Bilbao 2017.csv, and check the format and order of the columns in the file. So we'll open that file. The columns are detector ID, timestamp, and count. The ID of this detector matches with the name in Aimsun Next. The object type is detector. The initial date is 16th of April of 2017, and the real dataset starts at 6 AM, and the format is daytime ISO format. The first line of the file is the header, so I can skip the first line from reading. The column separator is comma, and the decimal separator is system1. So I will add three different columns here, which correspond to the ID, which is the name, the time, which is the time format that we have set up here, and the third column regards to the count. Then I will press OK. In the project folder, right-click Detector Data AM 6 to 10 with 15-minute resolution object and select Retrieve. If there are no problems with the file, the Real Dataset icon will turn blue. Any errors will be displayed in the log window. The Check Real Dataset dialog is also displayed. In this dialog, you can run various optional checks on the data's consistency, individual, congestion, and spatial. For more information, please have a look in the Aimsun User's Manual. So now close the window and let's move to the second exercise. In the second exercise, we need to generate simulated data with a static assignment scenario to compare with our real dataset. So select Project, right-click, New, Scenarios, and then Static Assignment Scenario. A new Static Assignment Scenario object will be created under the folder Scenarios. Open the new scenario to display the static assignment dialog. Make sure that the date in the scenario matches the date defined in the real dataset. In our illustration, this is 16th of April of 2017, but you might be using a different date format. For traffic demand, select Original Demand AM, and for transit plan, select PT plan. Note that your versions of Aimsun Next 20 might say public transport rather than transit, depending, of course, on your preferred language. For master plan, select Master Control Plan AM, and for real dataset for validation, select Detector Data AM 6 to 10 AM. Then click on the Outputs to Generate tab and activate the Section and Turns Store in Database option. Also, keep in memory results of the path assignment, and then click OK. Now we need to create a static assignment experiment. We can right-click here and create a new experiment. The assignment method that we will use is the Frank and Wolf assignment. Open the static assignment experiment and enter the maximum iterations to be 100 and the relative gap, reduce it to 0.01%. Activate the conjugate Frank and Wolf method for better and quickest results and press OK. Now we need to create two path assignment objects in which to store path assignment results. In the project folder, right-click on Demand Data, New Path Assignment Object, and create the first path assignment object. Repeat this process, but now just right-click on the path assignment folder and click on the new path assignment. Now you have two new path assignment objects in which to store both path assignments, all paths and the subset of the three most used paths per OD pair. Rename these objects as path assignment static all and path assignment static 3 most used. Open the static assignment experiment and click the Outputs to Generate tab. Tick the box Store Path Assignment, and for Path Assignment, select the Path Assignment Static All. Then tick the box Store Subset, and for Path Assignment Subset, select Path Assignment Static 3 Most Used. Then click OK. Right-click on the static assignment experiment and select Run Static Traffic Assignment. When the experiment completes its simulation, the results of the static assignment are visualized in two-dimension view window as shown here. The assigned volume view mode is automatically selected when the experiment finishes. A new dialog containing the static assignment results is displayed. Let's continue with exercise number 3, comparing assigned volumes to real observed data. Here, we will use a dialog containing the static assignment experiment results to compare our simulated data to the real dataset. Click the Sections tab and carefully check the flow, assigned volumes, cost, distance, speed, time, and volume over capacity ratio, calculated in the final iteration. You might find it useful to sort the columns by higher or lower value. To see all values clearly, you might need to resize the dialog by clicking and dragging its edges. Make similar checks for the tabs Turns, Connections, Supernode Trajectories, and Subpaths. Click on the Convergence tab and verify that the relative gap percentage is sufficient according to the requirements of the project. It is both available in table and graph mode. Click the Validation tab and compare the results with the real dataset Detector Data AM from 6 to 10 AM. Click to the Show Regression Graph button to view the distribution of assigned versus observed flows between 8 and 9 AM. In terms of results, initially we obtain an R-squared value of 0.96, which shows that there is a high degree of correlation between the observed and assigned values. This is a good result. However, the slope of the line is below 1, with a value of 0.85. We can see from the red line, which indicates that the observed counts in detector locations are for low volumes, less than 2,000 vehicles, lower than the assigned volumes, and for high volumes, more than 2,000 vehicles, higher than the assigned volume. This happens because the current observed counts were obtained in 2017, while the traffic demand OD matrices data were based on a 2010 survey. Also, the model was validated with more recent data from 2013. Since then, there have been a few changes in the traffic routes between 8 and 9 a.m. Traffic usage on highways has decreased, while the traffic on arterial roads has increased. This macroscopic model is considered sufficiently calibrated in terms of global and local parameters used in the volume delay functions, turning penalty functions, and junction delay functions. Next exercise, we need to define a subnetwork as our ongoing study area. Now let's continue with exercise number 2, where we will define a subnetwork study area and run a static traversal. To focus our study on the area around the scheme, we will create a subnetwork and run a static traversal to create the origin-destination matrices for the subnetwork. In a real-world project, we would consider the following types of information provided by external sources and then review the project documentation to check that the proposed study area is properly defined, verify the congested sections of the study area because congestion at model boundaries should be avoided. We might need to extend the study area around some entrances and/or exits of the model. Check the current map of detectors in the study area. We need to include the maximum number of detectors in the study area and might need to extend the area of the subnetwork in some cases. In our example, let's assume that after a discussion with the client and third parties, we finalize the study area shown below. The area is marked out by a black polygon with square vertices. To define a subnetwork, click on the tool Create a Polygon on the left side in the toolbar. Draw the polygon by clicking its vertices at the required points, and to finish and close the polygon, just double-click to add the final point to complete the shape. Click on the polygon in the 2-dimension view to highlight it, and then right-click Convert to Subnetwork. A subnetwork object is added to the project folder. Open this new subnetwork object and rename it to Subnetwork Hybrid Meso-micro. You can change the color and other options in this window. Now let's run a static traversal. We will generate a static traversal to create the OD matrices for the subnetwork. The new OD matrices will be based on the static assignment results generated in exercise 1. We will then run a static assignment scenario of the subnetwork and review the traversal matrix outputs. In the project folder, right-click Subnetwork Hybrid Meso-micro and generate a static traversal. In the traversal dialog, select the input parameters shown here. OD matrices for current track, traffic demands, and transit lines with the transit plan will be automatically generated for the subnetwork and added to the subnetworks folder, as shown here. To highlight the subnetwork in the 2-dimension view, right-click anywhere in the 2-dimension view and select Filters, Subnetwork, Hybrid Meso-micro. To verify the static traversal demand, we will test them in a new static scenario. In the project folder, right-click Subnetwork Hybrid Meso-micro, New, Scenarios, Static Assignment Scenario. Rename the scenario to Static Assignment Scenario Subnet and complete the parameters on the main tab. Set the date, the traffic demand, the transit plan, the master control plan, and the real dataset, and click OK. Right-click on the static assignment scenario subnet and create a new experiment with the assignment method Frank and Wolf assignment. Open the experiment and rename it to static assignment experiment subnet. And set the number of iterations and stopping criteria as in the exercise number 1. Right-click on the experiment object and select run static traffic assignment. When this assignment is finished, a dialog with the simulation results will pop up. Click on the Validation tab and select the shown regression graph. The static assignment result looks consistent with the results from the larger model. In exercise 3, we will check the detection coverage. It is important to know whether the available detection data sufficiently covers the traffic network conditions in the subnetwork. To find out, use the detector location feature to check the current coverage of detectors. This knowledge can help you decide whether to move or add new detectors to the network to cover all relevant conditions. In a real-life project, economic and other practical factors might influence decisions about the number and location of detectors. For step 5, you need to know the names of detectors in the subnetwork. You can see them by switching to the view mode Detectors in the 2-dimension view. So in the project folder, right-click, New, Infrastructure, Detector Location. A new detector location object under Detector Locations will be created. Open the detector location and, in the macro experiment, select the static assignment experiment subnet. Tick maximum percentage of vehicles to detect and set the value as 100. For a real-life project, this value might be smaller due to economic reasons or other project restrictions and guidelines. In the Detectors group box, select the detectors in the subnetwork from the existing detectors column and click the green arrow to move them into the included in the calculation column. And then click OK. In the project folder, right-click, Detector Location, Run, Calculate Detector Location to show the results. According to the results below, the percentage of detection coverage is around 87%, which is considered sufficient in this particular case. By adding more detectors, the cumulative intercepted percentage will be increased. In exercise 4, we will extend the OD matrices based on traffic measurements. Because the observed counts in the real dataset include 4 hours worth of data from 6 to 10 a.m., with a time interval of 10 minutes, we need to extend the 1 hour available traffic demand to cover a 4-hour period. To do so, we need to calculate the weight coefficient to extrapolate from the original traffic demand, which equals to 27,611 vehicles. So by processing the observed counts from 6 to 10 a.m., the result is 246,372 vehicles. We will divide the total trips of these observed counts by the total trips of the observed counts from 8 to 9 a.m., which is 67,590 vehicles. The result of this division is 3.65. So the resulting weight needed to multiply the seed OD matrices of the original traffic demand is 3.65, a factor of 365 applied in the demand. Make a copy of the existing traffic demand and double-click on it. Change the initial time from 8 to 10, change the initial time to 6 a.m. and with a duration of 4 hours. Extend the OD matrices for car and truck to cover the 4-hour simulation period and apply the 365 weight factor to this traffic demand item. And then click OK. Now let's use the extended OD matrices with a static assignment scenario. Right-click on the existing scenario static assignment scenario subnet and click Duplicate. A copy of the static assignment scenario subnet is created. Rename the duplicated scenario and experiment. Open static assignment scenario subnet 4 hours and select the traffic demand from 6 to 10 a.m. and click OK. Right-click on the Static Assignment Experiment subnet and run the Static Traffic Assignment. Select the Validation tab and press the Show Regression Graph. In exercise 5, we will adjust the subnetwork OD matrices. Because the OD matrices we have used so far are based on data from 2013, we need to adjust them so that they align more closely with the real data set from 2017. To do this, we will run a static OD adjustment scenario on the OD matrices and then run a new experiment. Let's see how we can run a static OD adjustment scenario. First step, right-click on the subnetwork hybrid Meso-micro, New, Scenarios, and create a static OD adjustment scenario. Open the new scenario and rename it to Static OD Adjustment Scenario Subnet and set the date. Set the traffic demand, the transit plan, the real data set, and the master control plan. Right-click on the subnetwork and select New Path Assignment. A new path assignment object under the subnetwork has been created. Open the new path assignment object and rename it to Path Assignment Subnet. And click OK. Right-click on the centroid configuration object and create a new OD matrix. Open the matrix and rename it to Deviation Matrix. In the Contents field, select Maximum Deviation. Click the Cells tab and for Operation, select Add. In the Add field, enter 100. For Condition, select All and tick the Apply to Empty Cells, and then execute, and then click OK. Now let's run a new static OD adjustment experiment. Right-click on the static OD adjustment scenario and select New Experiment. Accept the assignment method of Frank-Wolf and click OK. Open the experiment and rename it to Subnet. Then modify the target R² to 1 and the target slope to 1. Reduce the relative gap percentage to 0.001% and activate the conjugate Frank-Wolf method. Then click the Adjustment Constraints tab. In the Demand Elasticity group box, set the matrix elasticity factor to 0.55 for both vehicle types. This parameter controls by how much the values in the adjusted matrix might vary as the adjustment scenario proceeds. In the Demand Bounds group box, select the deviation matrix for both car and truck. And then click OK. In the Outputs to Generate tab, tick the box Store Path Assignment and select the path assignment file that we created in exercise 5.1. And then click OK. Right-click on the Static OD Adjustment Experiment subnet and run the experiment. On the Results dialog, click the Outputs tab and then on the trips, compare the number of trips for each OD pair by activating the regression plot. Then click again on the table view and sort by relative difference to verify that the maximum and minimum values are under plus -100. Sort by original demand to see the most important OD pairs. If a specific OD pair has changed more than the desired value, you can find the OD pair in the deviation matrix and reduce the value from 100% to, for example, 50%. Click the Trip Length Distribution tab. The result looks good, so there is no need to modify matrix elasticity or trip length distribution. Compare the assignment outputs with the observed counts from 6 to 10 am. Click the Validation tab and check the comparison between the adjusted and the reference values. Now, create demand and matrices and check that 3 new objects have been created. These should be 2 new 4-hour OD matrices, car and truck, and 1 traffic demand with the new OD matrices assigned to it. In exercise 6, we will create a profile demand with a static OD departure adjustment. To obtain the required profile demand, the static flat demand from 6 to 10 am needs to be distributed through smaller intervals across the time period. A static OD departure adjustment can be used to profile the original static matrix automatically. We want to reproduce the observed traffic counts specified in the real data set per interval, staying as close as possible to the original number of OD pair trips for the whole period. It is important to start the process with a calibrated demand that fits the detection data for the full modeled period. The static OD departure adjustment does not calculate any new assignment. It takes previously calculated fixed paths from a path assignment produced earlier, plus link, section, and turn travel times, and uses them to calculate the assigned number of vehicles for each period. So let's right-click on the subnetwork hybrid Meso-micro. Select New and Path Assignment Plan. Open the new plan, rename it to Path Assignment Plan Subnet, set the initial time to 6 and the duration to 4 hours. Add Path Assignment item and add the Path Assignment subnet that was created previously. Click then OK to the Path Assignment Plan dialog. To add the required scenario, right-click on the Subnetwork Hybrid Meso-micro, New Scenarios, and then Static OD Departure Adjustment. Open the scenario, set the date, the traffic demand, and the warm-up period of 30 minutes. The path assignment plan, the one that we just created, and the real data set, and click OK. Then right-click on the scenario and select New Experiment. Open the experiment, rename it to Subnet, and in the demand bounds group box, make sure that the max deviation matrix column contains both car and truck matrices. For max deviation value, select percentage, and then click OK. Right-click on the Static OD Departure Adjustment Experiment subnet and run a Static OD Departure Adjustment. Once it is finished, add and the results dialog is displayed, view the trips and validation tabs. Check the regression line graph results per interval to verify the result for all intervals. Click the Trips tab again and click Create Demand and Matrices. Many new profiled matrices are created and added to the project folder in the Subnetworks folder. In exercise 7, we will run a Microscopic dynamic user equilibrium experiment loading static paths. In this exercise, we will run a DOE Microscopic simulation to obtain a new set of paths. We will be using the subnetwork we created in exercise 2. Right-click on the subnetwork hybrid Meso-micro, New Scenarios, and create a new dynamic scenario. Open the scenario and rename it to subnet, and complete the parameters as shown below. Don't forget to go to the Outputs to Generate tab and modify the statistical interval and the detection interval to 15 minutes, as the real dataset interval is also 15 minutes. Right-click on the scenario and select New Experiment. Select Microscopic Simulator, and the assignment approach, select Dynamic User Equilibrium and press OK. Open the experiment and rename it. On the Main tab, set the using warm-up period to 15 minutes, so that the simulation starts with traffic already circulating throughout the network. Click the Dynamic Traffic Assignment tab. In the Dynamic User Equilibrium group box for Do Not Consider Paths with the percentage below, enter 3. This means that only paths with more than 3% share over the total share per OD will be taken into account during the iterations of the DOE process, and then click OK. Right-click on the subnetwork and select New Path Assignment. A new path assignment object has been created. Rename it to Path Assignment DOE Subnet. This is where path assignment statistics will be stored. Right-click on the Meso DOE Experiment Subnet New Result. Rename the result to Result DOE. In the Outputs to Generate tab, tick the box Store Path Assignment, and in the Path Assignment field, select Path Assignment DOE Subnet, and then click OK. Right-click on the result DOE Subnet. Before we run the DOE, we have to go to the Profile Demand and check that the duration is 4.5 hours. The desired initial time is at 6 AM to 4. Now we need to access the Profile Demand and remove, by holding the Shift button, the 4 intervals from 5:30 to 6 matrices that were generated by using the static OD departure adjustment when we set the warm-up period to be 30 minutes. And then we click OK. So now we have a demand with initial time 6 a.m. and duration 4 hours. Now right-click on the result DOE subnet and run batch simulation. The simulation control bar is displayed at the top of the main window while it is running. Click the information icon I to show the result dialog in progress, and click the relative gap tab to see the evolution of the relative gap for each time slice. The time slice is determined by the dynamic traffic assignment tab, experiment level, and the parameter is called interval. Click the Vehicles per Iteration tab to check the number of vehicles that are waiting to enter inside the simulation or outside when the simulation has already finished. This indicates whether there are any potential gridlocks in the simulation that might cause unexpected virtual queues. DOE simulation has already finished. All the time intervals have reached the target relative gap percentage, which was 0.5%. Now let's check the validation tab. The comparison of the counts between the result DOE and the detector data has a very good shape. Because there is no information about the congested sections in the network, in a real-world project we might need to ask for this information to be provided so that the model emulates real traffic conditions. This applies not only to counts but also to speed and/or delay times. To check global traffic conditions in the model, select the view modes, simulated speed and simulated delay time, and play back the simulation for its view mode to visualize results in 15-minute increments. In exercise 8, we will run a microscopic stochastic route choice scenario loading DOE dynamic paths. In this exercise, we will simulate a microscopic stochastic route choice experiment using a percentage of the path generated from the previously obtained DOE results. First, we will set up the scenario and experiment. Then we will check and compare the results. To set up the scenario and experiment, we will right-click on the Subnetwork hybrid Meso-micro, new, and create a path assignment plan. We'll open the path assignment plan and rename it to path assignment DOE. We'll set the initial time with a duration of 4 hours and then add the path assignment item. In this case, we will add the path assignment DOE subnet. Right-click on the Subnetwork hybrid Meso-micro and create new scenario, dynamic scenario. Rename it to dynamic scenario subnet using the DOE paths and set the following parameters. Don't forget in the Outputs tab to modify the statistical interval for statistics and for detection to be consistent with the real dataset, and then click OK. Right-click on the scenario and create a new experiment. For network loading, select Microscopic Simulator, and for assignment approach, select Stochastic Route Choice. Double-click on it and rename it to using DOE paths. Set up 15-minute warm-up period and go to the dynamic traffic assignment and set the following parameters. The fixed routes group box indicates that 70% of cars and 90% of trucks will follow the path assignment. The remaining trips will follow the OD routes that are calculated based on the dynamic cost functions, which update the costs every interval, in this case 15 minutes. Lower down on the dialog, the maximum paths to use from input path assignment value is 3, and the maximum paths per interval is 5. This means that 2 alternative paths will be calculated as well as the 3 paths available per OD pair in the path assignment file. So in total, 5 paths. Click OK. Then right-click on the experiment and select New Replication. Open the replication and rename it to Replication using DOE. Right-click on the replication and run batch simulation. While the simulation is running, check the log. A message which says path assignment results have been retrieved from file.apa is shown in the log window. It is time to check and compare the results of the simulation. When the replication is complete and the dialog containing results is displayed, click the Validation tab and then the Regression Graph button. The result looks very good, with a R² of almost 1 and a slope of almost 1. As well as the R² plot and the slope, we can check the root mean square error criteria, which in our case is equal to 0.1. The smaller the RMSE, the better the model fits. Another validation criteria that is commonly used is the GEH formula, which compares hourly traffic counts to hourly simulation output. Staying on the validation tab, change from 8 AM with a duration of 1 hour, hit the option Action, calculate GEH. A view mode named GEH statistic for 34150 replication using DOE paths is created. You might need to move the replication results as I did to see the view mode better. This view visualizes using a color range the quality of the detector's data. Display the legend for further details. Windows, window, legend. So we see that most of the detectors in our network have a good fit, and some 2 detectors actually require further investigation. Now let's see the GEH summary on the bottom of the dialog with a number of objects. In our case are detectors, 17, and the number of objects with GEH less than 5, 15 detectors. And only 2 detectors have a GEH less than 10. In most projects, the minimum GEH criteria is defined as GEH less than 5 to be 85% of the detectors. If you want to make further checks, you can verify that all hourly intervals meet the acceptable GEH criteria. We will now compare the data from result DOE subnet with replication experiment using Meso-DOE paths. From the Data Analysis menu, select Data Comparison to open its dialog. From the reference list, select Result DOE subnet, and from the compared list, select Replication using DOE paths. Remove the object's turn from the comparison and click Compare to display the results. Click the graph or the table icons to change the visualization of the data. To compare the same outputs in the form of time series, from the Data Analysis menu, select Time Series Viewer. One at a time, click on the results you want to view in the Subnetworks folder and click Add Series. The screenshot below shows a comparison of the average simulated delay time per interval. In exercise number 9, we will run a Meso-micro hybrid scenario loading dynamic paths. In this exercise, we will run a hybrid simulation that combines a simplified mesoscopic simulation of much of the model with a more detailed microscopic simulation of a critical area where the study focuses on a tram route. First, we will create the experiment we need and then define a study area for the microsimulation. Let's create the experiment. Right-click on the dynamic scenario using DOE paths and create a new experiment. In the experiment type dialog, select Meso, Micro, and Stochastic route choice. Open the experiment and rename it Set 15-minute warm-up period, and then click OK. A warning will pop up as no microsimulation area has been defined so far. So let's create the microsimulation area. Click on the polygon button and let's create the microsimulation area. Right-click on the polygon and select Convert to Simulation Area. A new simulation area is added to the Simulation Areas folder. Rename the new object Microsimulation Area. Open Experiment Hybrid Meso using DOE paths and click the Hybrid tab. In the Simulation Areas group box, tick Micro Simulation Area. Click the Dynamic Traffic Assignment tab and complete the parameters as shown here. And then click OK. Right-click on the experiment and select New Replication. Rename the replication and right-click on the replication and run batch simulation. When the replication is complete, the view mode Simulated Flow is selected. As in exercise 8.2, use the data comparison feature to compare experiment hybrid Meso-micro, to compare the replication hybrid using Meso DOE paths with replication micro using DOE path. Remove the terms, objects, and compare. We see that both simulations give us almost similar results. We will now compare the speed statistics for a grouping of all the sections inside the microsimulation area. Right-click on microsimulation area and select objects inside. The internal sections are now copied and ready to be added to a grouping. In the project folder, right-click on Data Analysis, New Grouping Category. List of objects of type, select Section. A new grouping category has been created. Right-click, New Grouping. Grouping Sections Microsimulation Area and Add Selection. So all the selected objects have been imported in this list. Now click OK and right-click on the grouping and press Refresh Statistics for the replications you would like to compare. Then double-click on it and check the time series tab. Let's compare speeds. We see that both simulations, the speed in kilometers per hour is almost similar. Let's adjust the limits from 0 to 40 kilometers per hour. In exercise 10, we will run a macro-meso hybrid simulation. In this exercise, we will run a hybrid simulation that combines macroscopic and mesoscopic network loading. We will model the city center at a mesoscopic level and the outskirts at the macroscopic level. The exercise is quite long and is broken down into 6 stages: defining the area and checking cost, adding a scenario and running the experiment, changing the volume delay function to a BPR function, adding a path assignment plan, splitting the traffic demand, and running the final experiment. First, let's define the area and check the costs. We will define the area we want to include in the meso simulation. We will also check to ensure all cost functions use the same units. Click the polygon, create a polygon button, right-click, remove the filter, and let's create the subnetwork. Right-click on the polygon just created and select Convert to Simulation Area. Rename the new area as a Meso Simulation Area. Now we need to check our cost functions. Route choice is assigned when a vehicle is generated, whether its journey starts in the macroscopic area or in the mesoscopic area. The cost of route choice paths is the sum of all the volume delay functions, turn penalty functions, and junction delay functions from the macroscopic area, plus the initial or dynamic cost function from the mesoscopic area. We must check and ensure that the units across the network are the same or converted if they are different. This means that all cost functions should give the cost in minutes, for example, rather than a mixture of minutes and seconds. In the project folder, click Demand Data Functions. Here we can reveal the list of all functions being used. For volume delay functions, turn penalty functions, and junction delay functions, follow these steps. Double-click on a function to see the full details. The example shown, click the usage tab to see if and where the function is used. Then click the main tab to see the function code. We can see in the code that the cost is the estimated travel time given by the volume function. This is given in minutes by default. Check and make sure that all costs in all functions being used are also expressed in minutes. The default cost function for Meso, which can't be accessed from the interface, uses seconds as a unit. We will therefore need to specify the conversion in the scenarios experiment. Let's add the scenario and run the experiment. Click Scenario, New, Dynamic Scenario, open the new scenario, rename it to Macro-meso Dynamic Scenario, and set the traffic demand as we did before. Then click OK. Then go on the outputs generate and modify the statistic interval to be 15 minutes. Right-click on the Macro-meso scenario and create a new experiment. For network loading, select Macro-meso Hybrid Simulator, and for assignment approach, select Dynamic User Equilibrium. Open the experiment, rename it to Hybrid Macro-meso DOE Experiment, and click the Hybrid tab. Select the meso simulation area. In the cost group box, leave the volume delay function unit conversion factor as 60. This ensures that all the functions will use minutes for units. Then click OK. Right-click on the experiment and create a new result. Rename the result to Result Macro-meso DOE and click OK. Right-click on the result and run batch simulation. When the result dialog is displayed, we can see that convergence is not reached within 20 iterations. This is due to the volume delay functions used, which are per row type. We should change all volume delay functions to the BPR function, which is also measured in minutes. Let's change the volume delay functions to BPR functions. Click the letter T on your keyboard to activate the table view. Then on the object type, select Section. Scroll to the extreme right of the table until you reach the volume delay function. At the very bottom of this column, underneath the left-right scrolling bar, there is a cell that affects all the cells above it. In this cell, click and select BPR standard to change all volume delay functions in the column to the BPR. Let's close the table view. We will now add the path assignment plan using the paths from the static assignment. The path assignment plan will contain two path assignment items. Path assignment static 3 most used, which is twice used, at the start and the end of the duration. On the demand data, click New Path Assignment Plan. Open the path assignment plan and rename it to Path Assignment Plan Macro-meso. Add path assignment items. So in the first 15 minutes, from 8 to 8:15, only the 3 most used routes will be used. In the next half an hour, only all the routes included in the path assignment file will be displayed. And for the last 15 minutes, again, the 3 most used routes will be used. And then click OK. To better represent the peak traffic, we will split the traffic demand. We are aiming to split the traffic demand into 4 OD matrices, each for car and truck, spread across the 1 hour duration. We will give each matrix a percentage factor in line with the following table. Right-click on traffic demands and create a new traffic demand. Rename the traffic demand to original demand AM profile. Set from 8 and for 1 hour the duration and add a demand item. So we will use the same OD matrices but modify them by multiplying a factor every 15 minutes. So first I will import all of them and then I will apply the percentages by changing the 100% to 20% during this interval, 30% during the second interval, 27% during the third interval, and 23% during the fourth interval. The same I will do for tracks. Okay, I'm done. Then I will click OK. Now let's run the final experiment. We will open the hybrid Macro-meso DOE experiment. On the main tab, for using warm-up, select Use Scenario Demand from the drop-down list and set the time alongside as 15 minutes. Click the Dynamic Traffic Assignment tab and set these parameters. Set the number to intervals 2 and increase maximum iterations to 30. Right-click now on the result and run batch simulation. On completion, we can see that the relative gap now converges at iteration number 16. Thank you very much for listening to me, and I hope you enjoyed this tutorial.